This is the third installment of quantum mechanics. We'll be discussing models of the atom. You recall from our nuclear physics unit that we had something called the Rutherford Model of the atom. It's a small positively charged nucleus at the center. Electrons orbit the nucleus, kind of like planets orbiting the sun. They're kept in orbit by the electrostatic force. Unfortunately, the problem with this is that Maxwell's equations predict that an accelerating charge like this would very quickly radiate all its energy out in the form of electromagnetic waves, spiral down onto the nucleus, and then you have no more atom. Since that's obviously not what happens, that's a big problem. Another problem with it comes from something called the emission and absorption spectra of elements. The idea is that if an atom is hit by some light, it takes some energy from the light, and one of the electrons then moves up to a higher energy orbit. And kind of like with gravity in orbits, that means that it orbits further from the nucleus. And if the light has enough energy with it, it knocks the electron all the way off, which explains the photoelectric effect that we discussed previously. The other thing that can happen, if you've got an electron in a high energy state, it can move to a lower energy orbit by emitting some light. So it loses some energy when it moves to a lower orbit. That energy gets taken out as light. And you can make something called an emission spectrum. What you do is you pass an electrical current through a gas, sparks, and what that does is the electricity moves electrons up to higher orbits. When they fall back down, they emit light. And then you take that light and you pass it through a prism. Splits it up into the various colors, and different elements turn out to make different sorts of spectra with different characteristic colors. It turns out that if you have a particular element, only certain frequencies are emitted from a particular element, and what frequencies are emitted are kind of the fingerprint of that element. So right here, this is the emission spectrum for hydrogen. Hydrogen has 4 lines in the visible spectrum and 1 in the near ultraviolet, which can sometimes be seen if it's a very bright spectrum. It's got a red line, it's got a greenish blue line, and it's got a blue line and then 2 purple to ultraviolet ones. They range between 400 and 650 nanometers in wavelength. That's one of the things you're going to observe with the spectrometer that you're going to make, is you're going to look at emission spectrum of elements and see how you can determine the element from the fingerprint. The other thing that you can make are absorption spectra. We talked about this with global warming, with the colors of light that are absorbed by the atmosphere. The atmosphere absorbs infrared, but not very much visible. But in this one, it's kind of the reverse. You take a gas, hydrogen for instance, and you put a light behind it. And some of those colors of light will be absorbed by the gas, and the rest will pass through. And then you'll get a picture that looks like this. This is the absorption spectrum for hydrogen. And those black lines, those are the frequencies that are absorbed. And it turns out that the frequencies that are absorbed in the emission spectrum are exactly the same frequencies that are created in the emission spectrum. But the thing is, Rutherford's model of the atom cannot explain why only certain colors are produced. It would predict that all colors are produced by all atoms. So back to quantization. Remember, we talked about quantization before. We said that light carries energy in discrete packets called quanta or photons, and they're proportional to the frequency. Remember, the energy of a photon equals Planck's constant times the frequency of that photon. Because of that, the discrete spectrum with only certain colors implies that only certain amounts of energy can be emitted at a time. And that means the electrons are limited to just a few energy levels. And when an electron moves from one energy level to another, it emits light. They emit exactly one photon when they move between energy levels, and that photon has an energy equal to the difference between the energy levels. So the energy of the photon equals the change in the electron's energy. So if only certain photon energies are emitted, that means only certain electron energies are allowed. And we can diagram those energy levels by looking at these spectra. First thing you do is you take all the wavelengths of light that are emitted, and you calculate the amount of energy corresponding to each of those wavelengths. And then from that you can figure out what energies are allowed to the electrons. In the case of hydrogen, we have an infinite number of energy levels, although only a few of them are important. You have the ground state, the lowest allowed energy. And the energy of the ground state is negative 13.6 electron volts. We say it's negative because that's compared to a free electron. An electron just floating out there in space by itself has an energy of 0. So this is a free electron up here at 0 energy. The next energy, the n equals 2 state, we call this n equals 1, n equals 2 state, has an energy of negative 3.4 electron volts. Then there's the n equals 3 state, which has an energy of about I don't know off the top of my head what the energy is. I think it's about 1.7. And then you have n equals 4, n equals 5, and so on. There's an infinite number of energy levels, but they get spaced really, really close when they get towards 0. The lines you can see are the transitions where it jumps from a high energy state down to n equals 2. All of the transitions to level n equals 1 are in the ultraviolet because they're very high energy photons. For an energy to jump from any of these energy levels all the way down to here, it's got to give up a lot of energy, and that means a very high frequency photon. And then all of the transitions in here are infrared. There are very small gaps between those energy levels, and that means that the photon energies are very small, which means they're infrared, you can't see them. So the ones you can see are the transitions to n equals 2. The idea is that the energy of the emitted photon is equal to the difference between the two energies, and we show a transition by a vertical line drawn between the energy levels. You can also have photons absorbed. But a photon will only be absorbed if it's exactly the right energy to move a photon up to the next energy level. If you look at hydrogen spectrum, the hydrogen spectrum, if it's in the ground state, n equals 1, you have to give it at least 10 electron volts of energy just to get it to n equals 2. And that means that hydrogen electron in the ground state can't absorb long wavelength light, low energy. But if for some reason the hydrogen atom is already in its n equals 2 or n equals 3 states, it can absorb more energy to move up to even higher energy states. So, in an example of how you do this, you've got a particular atom that has energy levels of -11, -4, -2.5, and -1.8 eV. We want to find the wavelengths of light that can be emitted from this atom. So we'll draw an energy level diagram for it. -1.8, -2.5, -4, and -11 electron volts. Those are the energy levels. And so the photons that can be emitted from this are this one, which has an energy of 7 electron volts. This one that has an energy of 8.5 electron volts. So 7 eV, 8.5 electron volts. This one here has an energy of 9.2 electron volts. We've also got this one, which is 1.5 eV, 2.2 eV, and last of all, 0.7 electron volts. Those are the energies of light that can be emitted, but we're asked for wavelength. Remember, energy equals HF, but frequency is c over lambda, and lambda equals hc over E. So for the 7 electron volt one, lambda equals Planck's constant. We're working with electron volts, so we use 4.14 times 10 to the minus 15 EVS times 3 times 10 to the 8th meters per second. Move that out of my way. And divide by the energy, which is 7 eV, and that works out to be a wavelength of 177 nanometers. And if you compute the wavelengths for the other energies, we find other wavelengths of 146, 135, 828, 564, and 1774 nanometers. These three are all ultraviolet. This one and this one are infrared, and the 564 is green light. So the emission spectrum of this light, if you just looked at it with your eye, would look very green. If you want a challenge, you go the other way. You say, here's the photon energies, find a possible energy level diagram. And there's usually more than one possibility. So have fun with that. It's a challenge. And the whole thing with the emission lines allowed the creation of what's called the Bohr model of the hydrogen atom. It's very similar to Rutherford's model, except whereas Rutherford said any orbit is allowed, it just has to be elliptical, obey the 1 over r squared law and all that, Bohr said only certain orbits are allowed. The energy of the allowed orbits are given by something called Rydberg's equation, where the nth energy level is 13.6 eV times 1 over n squared. So E1 is negative 13.6 electron volts. E2 is negative 13.6 over 2 squared, which is 3.4 electron volts. Energy E3, negative 3, is negative 13.6 over 9, gives us 1.5 electron volts. E4 is 13.6 over 4 squared, which is 0.85 electron volts, and so on. Notice that as n approaches infinity, then the energies approach 0. And so they get very closely spaced at the top, just like we saw from the experimental energy level diagram on a couple slides back. This means that the photon energies, which are always the difference between two electron energy levels, are given by 13.6 eV times 1 over n squared minus 1 over m squared. N and m are integers. This is the difference between the nth and the mth energy levels. So the electron here is moving from the nth state to the mth state. And all the frequencies emitted by hydrogen have to fit this pattern for some integer values of n and m. Unfortunately, with the Bohr model, Bohr didn't explain why this should be. He was just saying, well, this is what we see. This is our model. Now we need to figure out why it does this. And that would have to wait until the 1920s or so for Erwin Schrödinger to come up with a better model. Now, quickly, an example. Electron in a hydrogen atom is excited from the ground state to n equals 3. Question is, what wavelength of light is required to do this? So the idea is it starts out with a low energy, and it starts out with negative 13.6 eV. It moves up to the third energy level, which is negative 13.6 over 9, which is 1.5 electron volt, negative 1.5 electron volts. And that means the photon energy is the difference between those, which is equal to 12.1 electron volts. And then we just say, okay, that equals hc over lambda. Lambda equals 4.14 times 10 to the negative 15th EVS. Divide by the energy, which is 12.1 eV. And that gives us a wavelength of 102 nanometers, which is well into the ultraviolet. And the excited electron, which starts out in the third energy level, then falls to the second energy level, which has an energy of negative 3.4 eV. And so that means the photon energy that's emitted is the difference between those two levels, which is 1.9 electron volts. And the wavelength, hc over E, has a wavelength of 653 nanometers, which is in fact one of the emission lines of hydrogen. Although because of rounding errors, it's actually closer to 655, but we can deal with that. Next time, we're going to try to explain why it is that only certain photon energies or certain electron energies are allowed.